In this video, we're going to introduce work, which is really a piece of energy that we've been really missing in a lot of our conversations. And by the way, this title slide is wrong. It says qualitative. This is a, well, actually, yeah. Well, we're kind of doing both. So it's a qualitative and quantitative approach. My slides are wrong. It'll be fine. Okay, so let's get into talking about work. So what we'll talk about is first we're going to have to define what work is. And then we've been using energy bar charts to track the flow of energy. And so we'll have to figure out how we're going to include that in our energy bar charts. And then last, there's going to be a question that's kind of brought up of like, okay, some things could be work or they could be potential energy. And so the question we'll have to try and answer is like when. When do I consider something work and when do I consider it potential energy? So that's the last thing that we'll get into. So the lesson goals are first, I want you to understand the definition of work, like what work is. And then second, you need to be able to represent work in energy bar charts. So that kind of goes along with our indicator of like energy transformations. So the idea is you need to be able to see where the energy is flowing, and that's what our bar charts are for. So that's what that goes along with, is identifying how work plays into transformations. And then the last thing here is you need to be able to determine when to use potential energy and when to use work. And that's, I think, a fairly simple idea, but if we're not explicit about teaching it, sometimes it gets confusing. So let's start with a little bit of a problem that I think will introduce why we need work. So we're going to do energy bar charts for a scenario here where Superman is pushing a train. Now I'm going to make the train the subject of my energy bar charts. And so Superman's going to push it from rest until it reaches a high velocity. So if I draw a little doodle to help guide me here, I'm going to start with a train that has an initial velocity of 0. And actually, I'm going to make that maybe velocity 1 so I don't get confused later. And then I'm going to see if I just do kind of two other locations, I'm going to have some velocity at point 2. And then at point 3, I'm going to have a higher velocity. So we're seeing that this thing is speeding up. Now, when I go to do my energy bar charts for this, what I'm going to see is that if I start asking my questions, right, in this first one, I have no energy. There's no height, there's nothing stretched or compressed, and there's nothing moving. So here there's just no energy at this first bar chart. At the other two, I'll definitely have kinetic though. So let me put like a little kinetic line. Now for this one, I have some kinetic energy. So there's some kinetic energy there. And then when I get to this third one, I'm moving faster, so I must have more kinetic energy. And this seemingly violates our law of conservation of energy, that I'm gaining energy from somewhere. I don't know where it's coming from. Now, we can represent this in an energy bar chart using non-mechanical energy. So maybe I could do it this way. I could say, okay, well, here I've got non-mechanical energy, and here I've got non-mechanical energy, and here I've got non-mechanical energy. And so maybe I could represent it this way and say, well, my non-mechanical is transitioning to mechanical. So maybe I could draw the bar charts like that to show the transition. And that's perfectly acceptable. But I have a problem of I don't know how to quantify non-mechanical energy. Like how can I calculate that, right? So like kinetic energy, if I had numbers, that's 1/2 mv squared. This is 1/2 mv squared. But I would need something to plug in here to be able to, set these equal and do all my energy conservation stuff. And I don't have anything. So that's a big problem for us. We can't do anything with this. And so what we need then is a new concept that we can use to figure out how to deal with this type of situation in a quantitative sense. And that idea is work. So work is just energy transferred, and transfer is a really key word there. It's energy transferred between objects via a force. So it's energy transferred via a force. Those are the key words. Transferred via a force. And what's interesting is you have to have displacement for work to be done. And if we're thinking in terms of energy being, kind of a quantity that describes motion, well, in order to have transferred energy, the thing must have moved. And so that's the first stipulation, is there must be a displacement. And the second thing is what we'll see is that we still have this idea of things that are 90 degrees apart from each other don't affect each other. And so a force will only do work if there's a component that's parallel to the displacement. So we have to look for a displacement and a component of work is parallel. Now, our energy, it could be adding energy or it could be removing energy. And so what we'll see here is that work, it could have a sign. So it could be positive if it's adding energy, or it could be negative if it's removing energy. Yeah. Okay, so if we look at the calculation bit, I don't want to get too in the weeds with the quantitative bit, but I think there's a little bit here that is worth discussing. So let's say you can see this line D here, that's a displacement, so that's a little dotted line. And then you've got a force vector here that is it's doing work on the object. And so what I want to do is here's actually the core mathematical equation for work. So you can see there's a force that's parallel. So there's a force that's parallel, and I only care about the parallel portion. That's what that little bit's there for. And there's a displacement. What I want to show you here is that this is the core equation, but if I try to calculate how much of the force is parallel, I'm going to get this equation here. So I'm just going to walk you through that real quick. So let's say this purple arrow is my force, and there must be an arrow here, or an angle here between the force and the displacement. Well, if I try to decompose this vector to get this kind of blue component here, then it's adjacent to the angle. And when I try to decompose it, I'm going to have the magnitude of the force multiplied by the cosine of the angle. And that's how we get this other representation here. So you'll see both of these in different places, and these two are interchangeable. They're equivalent statements. Just remember that this angle has got to be measured between the force vector and the displacement vector. Now let's talk about including work in our energy bar chart. So we're going to do bars as usual, so that part's staying the same. But what I'm going to do is I'm basically going to add in, so before we would have energy bar charts at different states. We'd be like, okay, state 1 and state 2 and state 3, and we're having bars and bars and bars, right? So that doesn't look like a bar. Bar. So that's how we would represent things, is each bar chart represents a single state. Well, what we're going to do for work is we have to consider, like, work is not done in an instant, it's done over a period of time. And so what we'll do is we'll insert bars for what's happening between the states. So what I'm going to do is I'm going to insert bars here for what's happening between states 1 and 2. And here for what's happening between states 2 and 3, so that I can represent energy that's added between those states. Now, I'll have to be careful here that bars are adding or subtracting energy between the states. Now, the adding or subtracting is important because when I represent those bars, simply put, an upwards bar is going to be adding energy, and a downwards bar is going to be subtracting energy. So you could think of above 0 and below 0, positive and negative. And we also remember that scaling is still really important here. We want to be roughly doing our bar charts to scale. So let's look at a quick example of this. So I've got Superman pushing a train from rest until it reaches high velocity. So the same example as before, but now I'm going to represent this using energy bar charts. So let me just do this off to the side. So I'm going to start with kind of the same doodle as before, right? So I've got a train that its velocity at point 1 is 0. Its velocity at point 2 is something. And it has a velocity at point 3 that is bigger. Now what I'm going to do now is I'm going to start with the same bars that I had before, right? So at state 1, I had kinetic energy, and there's none. There's no energy at all. Well, now what I'm going to do is before I jump to 2, I'm going to think about what's happening between steps 1 and 2. And what's happening between steps 1 and 2 is I've got Superman, who's pushing it. He needs an arm. Who's pushing it between steps 1 and 2. So during that time period, he's exerting a force, and his force is in the same direction. His force is that way. It's in the same direction as the displacement. And so his work must be adding energy to the train. He's doing positive work. And so I'm going to do is I'm first going to separate this with a dashed line. And I'm going to say that between steps 1 and 2, there was some positive work done by Superman. W sub S, work done by Superman. So now when I go to my next bar, and I'm actually going to use a solid line here, what I'm going to see is that now, when I draw that same bar as before, I'm showing that I have kinetic energy, but now I can see where it came from. I can see that, okay, I had none, and then I added this amount, and so now in this state, I have this much. So you have to see your bars between states as adding in energy, to where essentially the energy here is going to add up to the energy here. So to think about the bars just a little differently here, right? So this plus this equals that. That's one of the reasons I do a dashed line, is to communicate that those two are going to add together. So let's keep going to the next step, and what's going to continue to happen is that Superman's going to do more work. And I think it's reasonable if we took this about halfway, we could say he's going to do an equal amount of work. And so when I draw my energy bar chart, I'm going to draw an equal bar, right? So it's the same height as this bar, roughly, because it's an equal amount of work that's done. Now when I go, and by the way, this was a step between steps 2 and 3. Now when I go to draw my energy bar chart for step 3, I'm going to add these two up to get the third one. And so I've added this much, and this is the same height, so I should have a kinetic energy bar that is twice the height. And so now, because I've added in this concept of work, I can draw my energy bar charts where I'm seeing that there's energy entering my system. So each one of these bar charts is showing energy coming into my system, and thus the energy of that system, we can see why it's increasing. And we've shown an equation I can use to calculate this energy that's being done. So this is now quantifiable. It's not some like, non-mechanical energy came from somewhere. No, I can put numbers to it, I can calculate it, and it's very concrete now. So another example. Here we have kind of the reverse example. So Iron Man decides to show off and stop the train. Superman started moving. So in this case, we're going to have a train that is moving. So it starts with a high velocity, and it's going to slow down to where it's not moving anymore. So that's what we're focusing on for the next one. So here, if I start drawing my bar charts, and again, I'll draw my doodle to make sure I feel good about what's going on here. So I start at, not at 0. I start at some large velocity. In state 2, I now have less of a velocity. And in state 3, my velocity is 0. Well, now I can go back and think about this again, where I've got kinetic energy to start, and I've got a lot of kinetic energy to start. Right? So that's state 1. Now I'm going to draw the work done between states. So between state 1 and 2, well, Superman's here, right? He's pushing on it. Iron Man is. So Iron Man's pushing on it, and he must be pushing against it because he's slowing it down. So he must be pushing over here. It's little jet boosters or something. So he must be pushing over here to slow it down. And so that means that Iron Man's force, so F sub I, it must be working against the displacement. And so what I'll see here is that because he's working against the displacement, he's removing energy from the train. And we can see that clearly because it's slowing down. And so he must be doing negative work. So when I represent his work, I just kind of flip the bar. So I'm going to put the label on the other side, the work done by Iron Man, and I'm going to draw my bar there. And so that communicates that it's negative work done. So now when I do my bar chart for step 2, I'm going to add these together, but because it's negative, that's functionally a subtraction. So I'm going to remove, I didn't do a very good job. I wanted this to be about half, but so I'm going to remove about half of that energy. And so here's my bar now for state 2. Again for state 3, or sorry, between states 2 and 3, I should say. I'm going to see that Iron Man does more negative work, and I'm going to make it an equal amount of negative work, so that by the time I get to state 3, the train now has no kinetic energy. And again, now I have a way that I can see the transformation of energy, right? So I've got kinetic energy, and Iron Man is removing a little bit of energy via work. And then in the next step, he removes a little bit more energy via work until eventually I get to the point where I have no energy remaining because Iron Man took it all away. So I can track the transformation and I can understand exactly what's happening. Now, some of you that think ahead, you may have realized, well, if forces do work, gravity is an interesting example because gravity, like let's say I have a ball that it's going to fall. Well, previously we would say that there is gravitational potential energy here, and that gravitational potential energy becomes kinetic energy as it falls. But there's an equally valid way to think about this to say that, well, what if we just say there's a force of gravity and there's a displacement that's downward, and so the force of gravity is doing work? Well, that's actually a totally valid way to think about this situation. And the difference is going to be, how are we thinking about our system? And so you may remember I've talked about before, we have to be careful to think about potential energy not belonging to an object, but belonging to a system. And so what we'll see here is that if there is energy that is belonging to the system, and it never leaves the system, we communicate that with potential energy. If there's any energy crossing a system boundary, then we would call that work. So a really important tool here is going to be our system schema. So what we're going to look then is that potential energy is energy that stays within the system, and if there's work, that's energy leaving or entering the system. So for example, if I look back at these examples a little bit more intently now, well, I could do a system schema for this guy, and I could say, okay, well, I've got the train, I've got Iron Man, I'm interacting with probably the Earth, and I'm interacting with the track. And I can now intentionally try to map, okay, well, the train's interacting with Iron Man via that force, the force of Iron Man. The Earth is interacting with the train via gravity. The track is interacting with the train via a normal force. Now, if I then set my system boundary, if I define my system as essentially just the train, you can see that every one of these force arrows that crosses that boundary is an opportunity where work could be done. Now, these two forces don't do any work, and the reason for that is because they act perpendicular to the displacement. My displacement is this way, and gravity is down, and the normal force is exactly up. So they're exactly perpendicular, so no work is done through those pathways, but I can see there is work done by Iron Man. And that's going to be the defining difference, is there energy crossing the system boundary? If so, we call that work. So let's look at this in detail here with a quick example. So if I have a ball that's dropped from the top of the building, so the same example I was just looking at before, I could look at this two ways. One, where I'm including Earth in my system, and one where I don't. So let me draw a system schema. It's a really simple one. I have the ball. and I have the Earth. And between those two, there's a force of gravity. Well, I have two choices of system. I could say that my system is the ball and the Earth, and that's what we're going to look at first. And if I choose that system, then this force is within the system. And so whatever energy there is there, it must be internal and belong to the system. So I would draw energy bar charts using potential energy. And so this is going to be quick and sloppy, but I would have potential gravitational and no kinetic, and then I'd have, less potential gravitational and an equal amount of kinetic, and then eventually I'd have all kinetic energy. So if my ball and Earth are both in the system, I use potential energy to show that change. Now, if instead I'm looking at just the ball is my system, well, now the force of gravity is crossing that boundary. So that's now going to have to be considered energy crossing the system boundary, and energy crossing the system boundary is work. And so that bar chart would look like this. I would have no kinetic energy, and then I'd have work done by gravity, and then I would have an equal amount of kinetic energy, so dashed line, straight line, and then I would have again more work done by gravity, and then I would have here these adding up to be the full kinetic energy. Both of these are equally valid. Both of them are equally valid. It just depends on the selection of the system that you're using. So the system selection is extremely important when we use energy. Notice here real quick before we shut down for the day that the kinetic energy is the same. I'm seeing the kinetic energy the same. What I'm seeing differently is where did that kinetic energy come from? Here I would say that it came from potential energy, and here I would say it was it was work done by gravity. So really just two sides of the same coin. So quickly here, just to wrap up, if my slides will get along with me. In this video, we've defined what work is. It's energy crossing a system boundary. It's energy that is being transferred to an object. We've represented that in energy bar charts. And last, we've looked at the difference between when to use potential energy and when to use work. And the key question there is, what's my system? That is the question you have to ask. If your system includes if your system includes both objects that contribute to the potential energy's existence, then you use potential energy. If not, then you use work.